Good afternoon. I'm a graduated student from Munseng College, Hong Kong Island. I'm sure all of you have heard of a game called Mastermind. It is a game which aims at breaking the code set by your opponent within 12 trials. In my presentation, I'll introduce to you a systematic way to break the code within 10 trials. After that, I'll generalize this method for games with different number of colors and code length. Finally, I'll talk about the number of trials needed. The code breaking process can be divided into 4 stages. When a game starts, as we have no information about the code, we want to know which colors may be involved. After that, we'll identify which color is correct and further sort them into Group M and Group N. Here, Group M refers to the first 2 entries and Group N refers to the last 2 entries of the code. In the arranging stage, we'll arrange the 2 colors in Group M and N in the correct order, and finally we get the correct code. Now, let me introduce 3 rules. Sorting rule states that if our trial is in this form, then we know that there is alpha x in Group M and beta x in Group N. Here, the color 0 refers to a color which is known as not appeared in the code. The second one is partition rule. It states that if our trial is in the form XXYY, then we can interpret it as a combination of these 2 results, where the total number of red indicator and white indicators remains unchanged. The last one is transformation rule. It states that if the given hints are all white indicators, we can regard it as all red indicators after this transformation. Let me illustrate the above concept by this example. Assume the code is now BEFD. In the analyzing stage, we'll input all 8 colors in the pattern XXYY. But in trial 3, we get a total number of 4 indicators. Therefore, we can stop here and enter the identifying stage here. From trial 1, according to our transformation rule, we know that the trial BBAA will be awarded 1 red indicator. So we input BBBB, and we find out that B is actually the correct color in the first trial. So by sorting rule, we know that B is in Group M. Similarly, we know that G is a 0 color. So from trial 3, we enter EEGG, and we get 1 red indicator. By partition rule, we know that GGFF will also award 1 red indicator, so that they add up will get 2 red indicator in the trial EEFF here. So, in conclusion, up till now, we know that BE is on the left and DF is on the right. However, their ordering is still unknown yet. So, in the arranging stage, we want to find out this ordering. The 2 white indicator here tells us that the order DF is wrong. So we know that the ordering in Group N should be FD instead. Now we get the final answer, BEFD. After finishing the ordinary game, we come to the general game. Here, we introduce one more new concept, principal axis. It is a vertical line which separates the code into Group M and Group N. However, as the code length can be greater than 4, the principal axis may not necessarily be placed in the middle. As you can see, the same method can be applied to a general game. The only difference is that if the number of color is odd, then we need to input 1 more trial using only the remaining color. In this case, we may leave that color until all the other colors are sorted into groups. Consider the following game with code length 5 and 9 colors. In the first trial, transformation rule implies that BBBAA will be awarded 2 red indicator. As in trial 3, we know that E is a 0 color. We will input BBBEE to identify the correct color in this trial. Similarly, the application of partition rule is shown in trial 2, while the application of sorting rule is shown in trial 4. So far, the procedure is quite similar to the ordinary game, but in the arranging process, we would reduce a long code into a few smaller groups until they are as small as possible before we come to direct checking. Because as you can imagine, group M and group N can be both very large. So we need to break down a code. And this breakdown process can be accomplished by introducing extra principal x's and sort the colors into new subgroups. Of course, this can be done by applying sorting rule repeatedly, just like what we did in the identifying stage before. Now, we want to know the trial requires in arranging the code. Let Tn be the least number of trials required to arrange a code of length n in the worst case. From our definition, no matter where we place our principal x's, we must have T1 equals 0, T2 equals 1, and T3 equals 3. But how about the others? As we know that the trial required depends on where we place the principal x's. One natural question is that where should we place the principal x's so that the number of trial required would be a minimum? Here, we claim that this minimum is achieved when we place the principal x's as close to the middle as possible. And this result will be proved by the second principle of mathematical induction. When the principal axis is placed at the center, the sequence Tn can be defined by this recurring relation. So when t equals to 1, it suffices to check whether these two equations hold. For the inductive step, we assume that this statement is true for code length up to k. Since this statement is also equivalent to this inequality when the code length is k plus 1. So we want to show that this inequality is true. And this will be proved in the following 4 cases. Let's consider the first case. By the induction assumption, the equations marked in red here holds for code length equal or smaller than k. So we can substitute all 4 terms here in the first inequality by these 2 equations. After some simplification, we find out that the first inequality is equivalent to the last inequality, which is true from our induction assumption when the code length is k plus 1 over 2. The proof for the remaining cases are similar to this case and is omitted here. Now, as we know that the principal axis should be placed at the middle, we can define the sequence Tn by the expression appeared in the previous proof. Lastly, we want to find out how many trials we need in order to break the whole code. If there are p types of color and the code length is L, then according to our algorithm, the total number of trials required in every stage can be found. By summing up the number of trials in every stages, we get the maximum number of trials in the whole game to be this formula. Now, as our final example, let us go back to our initial problem. According to the above formula, we know that why we can always break the code within 10 trials in the ordinary game. And this is the end of my presentation. Thank you.